Yesterday, the software crashed while recording the video, so I do not know if we will actually be able to get this video through the whole lecture or not. We'll see what happens. I'm hoping it was just a wireless issue, so if the wireless connectivity drops, then I can't record the lecture at the same time. Okay, so just be aware of that. You may not have a video to back you up on this. So, active site chemistry. So what we were looking at within 7 is now looking at the larger enzymes and how these different things can end up interacting and working with each other. Okay, so there's a variety of things that we then break it down into and look at. We've got primary structure. So what is the actual sequence of your protein or your amino acid that generates your enzyme? Okay. There are certain amino acids that are going to be more important than others to the actual reactive site or in the active site. All of those amino acids are going to contribute to the protein folding, but some of them may be directly involved in the chemistry that the reaction is trying to catalyze. Okay, so we want to find out what amino acids those are. So that's looking at your primary structure. The next thing that we can look at is your secondary and larger structure. So how the protein folds and in what way does it fold. Okay, so there's a couple things that will pop up there. How does that take your primary structure amino acids and bring them into the active site? Okay. And then number 2, what happens with the protein itself to either wrap around your substrates or do other things? Okay. Facilitate kicking products out or sucking substrates in. The other thing that we can look at is the actual organic mechanisms. So what's physically happening? What's transferring electrons around within your active site to allow for that enzymatic pathway to occur. And then kind of the last thing that we'll talk about, probably not in a whole lot of detail, will be the actual specificity of your enzymes. Okay, so just a fun example to mention there, you can go through and isolate from orange peels, which some of you may or may not have done, limonene. Okay, limonene has a relatively simple structure. Okay, and it is chiral. If we change its chirality, okay, just at that one position, all we're doing is changing the arrangement in space of the atoms. You can take a compound from like limonene that smells like oranges, and that simple change now makes it smell like spearmint. Okay, exact same carbon backbone, exact same carbon structure, everything's added to the exact same positions, except instead of an atom being aimed forward, it's aimed away from you. Okay, so a very subtle change in space drastically changes how we interpret it. Okay, why? Well, we are chiral. Everything within our nose is chiral, which means it's going to interact with molecules slightly differently if they have different chiral atoms. And that's what this picture kind of nicely shows, is that if we have a chiral atom here, we have to have that perfect alignment. If I exchange the red and the yellow atoms, okay, now it doesn't fit into the active site anymore. Right, and there was no way I'd be able to spin or rotate that molecule to get it to fit into the active site. Okay. So it's a pretty important feature within our molecules. And then we'll keep going back to chymotrypsin as our example for all of this, just because that's what your textbook has, and that's the only images I've got to put it together. Okay. So, in our primary structure, we've got our chymotrypsin, which we've talked about already, goes through and catalyzes the cleavage of the peptide backbone around the phenylalanine and your tyrosine residues. Okay? So within the primary structure, what we'd want to do is figure out what amino acids are critical to that reaction. So one thing we could go through and do with the amino acid sequence is just start changing it. Okay? So one of the things that we can do is we can mutate how our amino acid sequence, and we can change each of those amino acids, or we can react them with something else. Okay, and then what we do is evaluate, did the activity change of the enzyme? If the activity has changed, well then that amino acid was really, really, really important. Okay, so we have to come up with some ways that we can selectively target particular amino acids. So there's 2 common ones that get mentioned for chymotrypsin because these target the amino acids that are relevant. You get DIPF, which targets serine residues, and what I like to call toothpick, which highlights histidine residues. So those 2 compounds will react with the serine or the histidine residues, okay, depending on which one you're looking at, and then that removes the chemistry of the serine or the histidine residue because it's now reacting with that molecule. Okay? So what we end up trying to see is what happens to the enzyme's activity. Well, if I put on an extra piece, if I put on the dip next to the serine, well, the serine has now lost its functionality because it's tied into that label. Okay? If I then try and run the chymotrypsin reaction and say, hey, does it actually cleave? Well, if it stops cleaving, what does that mean? That means serine was involved in the actual catalytic cleavage. Okay? It had some very important role to the reaction. Well, there could be thousands of serines, usually it's a little bit less than that, hundreds of serines within an individual amino acid chain. So we'd have to go through and selectively target each of those serines to say, okay, which one in particular was the one that was doing the chemistry. Okay? Very tedious process, but we can go through and do that. So it turns out when we look at the chymotrypsin activity that what they were able to find from the primary structure is the serine located at 195 in the amino acid chain is critical for the chymotrypsin activity. Okay? And the histidine located at amino acid residue 57 is also critical for chymotrypsin activity. Okay? And they can find that out by using this kind of labeling system. Okay? So those can go in and target those individual positions, prevents the reactivity. That means those two amino acids are hugely important. Okay? This is still primary structure because all we're saying is the residue at this position is somehow having a huge effect. Okay? If this is located within the active site, what does that mean about serine 195 and histidine 57? Okay, and the amino acid sequence, are they close to each other or pretty far away? That's pretty far away. If we now look to the active site, if we're saying both of those are involved in the active site, what does that mean? Somehow the protein is folding up to get the serine 195 next to the 57. Okay? So our secondary or tertiary structure is definitely folded up to kind of get back to that position. Okay? At this point, we don't know what that structure is. All we know is that those two residues are super important. So it's still primary. If we then go through and look at the secondary or tertiary or not quaternary, but our secondary or tertiary structure, and that's what they're attempting to show with this big fancy ribbon drawing, is that if we look really, really carefully, what they've done is highlighted your serine and they've highlighted this histidine. And you'll notice that they are very, very close to each other. Okay? One of the extra things that they ended up noticing by looking at the secondary or tertiary structure is that they have this aspartate ion that's very close within that active site as well. Okay? So by looking at that, they can then start to predict those amino acids are now involved somehow in the chemistry of this. Okay? How do they know that is the active site?
Because of reactivity.
Well, but reactivity doesn't tell you structure. So remember, to see the structure, we're not looking at a reaction. Okay? We freeze it, we isolate it in its frozen state-ish frozen in a crystal structure. Okay? And then we look at the solid crystal structure that is now immobile. Because if it's mobile, those things are moving so fast that it blurs our entire vision. Okay? We can't see it. Okay? So how do we know that that is the active site if we can't ever see that that's where the reaction is occurring? What's that?
Being close to each other?
So we could make some predictions. We know the histidine 57 and the serine, I already forgot the number, 195, okay, are involved in the reaction. So we would assume that they are close to each other. Okay? But how does that then allow us to know the aspartate's important to it? So we could look at the folding patterns that still brings it together, but how do we know that that's actually folding into the active site? Maybe those are just critical for folding the protein in general, and the active site is somewhere else.
Multiple X-rays.
Not even multiple X-rays.
So when they make a compound that's similar to the substrate or something?
So we could start to look at modeling. So when we look at our X-ray crystallography, we could look at the pockets within it. Okay. And what would we match those pockets to? The substrate. So what we would need to do is make some kind of molecule that is similar to our substrate that would also crystallize out. So if we go through this crystallization process, we can crystallize in a substrate that fits in the active site. Now when we go through and look at our X-ray, what do we have? We've got the substrate in the active site and the enzyme wrapped around it. Okay? So when we go through to crystallize, it may be that we're just crystallizing the pure protein, because that's all we want to see is what's the protein structure. But we may also want to see how it's acting on an active site. Okay, so we may try and fold in, or not fold in, but include in that crystallization process the substrate. Okay. Does that make things more difficult? Absolutely. Now not just crystallizing an enzyme, but you're crystallizing a substrate in at the same time. Those two things are in a dynamic environment. So if we try and crystallize in a substrate, it's usually not just adding the substrate in. What we're actually trying to do is covalently link it to something within the enzyme. Okay? So that hopefully that's now tied. Right? And then when we go through and look at the X-ray, we can hopefully see how it fits in there and then be able to predict what's going on with that reactivity, okay, or its structural effects. So that's how we move up into our secondary plus structure. So, more important to me, or sorry, are there questions? Okay. More important to me would then be what's actually happening within the active site. So you'll notice that we got this big sequence of pictures going through here with all these kind of graphical weird interpretations and very little structure. Some structure, but not a lot. Why would we not show the entire structure?
Because you wouldn't see anything? It's too much?
It's so much that we probably aren't going to be able to process it appropriately. So what we do is simplify down to just the amino acids that are relevant to the actual bond changing, and then we can go through and process from that. Okay? So that's what they're trying to show within this. Okay? So in our first drawing here, you'll notice that we have our serine. Okay? And our serine residue, as its R group, is, what's the R group?
Alcohol.
It's just,
CH2 alcohol.
it's that CH2 alcohol, and you'll notice that they don't show the CH2. Why not?
It's not going to interact with anything.
The CH2 really isn't going to do anything. It's the alcohol that's going to do the chemistry. Okay, so all they're trying to show is the simple groups. You'll also notice that we've got the histidine residue shown as well. Okay? So what they're now going through and doing is saying what has to happen in this process. Okay? The last piece that they've got shown down here happens to be the, any guesses? No, it's not the aspartate.
Is it the substrate?
It's the substrate. What we're looking at is the peptide backbone. Okay, there's your peptide bond between the carbonyl carbon and your nitrogen. Okay, there's your peptide bond. So what has to happen is that's a very, very stable bond due to resonance. The nitrogen can share its electrons in. We got a lot of stability through that double bond. So if we're going to try and cleave that bond, we have to destabilize that. Okay? So the process of destabilizing that is going to be exchanging a bunch of atoms. Well, one of the first things that happens is that we do have a nucleophilic carbon, electrophilic carbon, but we need a strong nucleophile. Well, serine isn't a particularly strong nucleophile. Why not? What's the definition of a nucleophile? It wants positive charge. Characteristic, we need to have lone pair electrons. Oxygen has lone pair electrons, but it's not a strong enough nucleophile. What makes a stronger nucleophile? What's the characteristic of a base? Charge. We need a negative oxygen. Okay. We could move to our acidic R groups, because those give us a negative oxygen. But what's the issue with our acidic R groups? Resonance stabilizes the negative oxygen. So those are horrible nucleophiles. Even though we have a negative oxygen, they're very bad nucleophiles because the resonance stabilizes the negative oxygen. So really what we want is some kind of serine residue, but we need to get rid of the hydrogen. Okay? Which means the serine needs to act first as, careful, we need to get rid of the hydrogen. It needs to act as an acid. What's going to react with an acid? A base functional group. What is histidine? A basic functional group. So in our first step, what's happening is our histidine takes the electrons away from the hydrogen. That now makes a very strong nucleophilic oxygen for our serine residue. Okay? You'll notice that we skip a lot of steps when we go through, particularly in biochem. Okay? Even in organic, when you got into carbonyl chemistry, very often we skipped a lot of steps because there's a lot of just repetitive things. Okay? Biochemists are much worse at skipping steps, and to the point where in some cases they're actually dead wrong. Okay? So kind of be careful around that. But what ends up happening is that that hydrogen now gets picked up by our histidine. The electrons now in that bond are technically associated with the oxygen, so we can take those electrons and we can now attack our electrophilic carbon. But then that carbonyl carbon has too many bonds, so what happens? We break the weakest bond we've got, which is the carbonyl carbon oxygen pi bond. So we break that pi bond to form our tetrahedral intermediate. Why is it referred to as tetrahedral?
Single bonds?
You look at the carbon that was involved in it, and it has 4 different things attached to it. Hence, it is a tetrahedral intermediate.
So you said the histidine takes the hydrogen from the serine? And
The
then
histidine
electrons-
takes the hydrogen from the serine.
And the electrons go to the oxygen, and then the oxygen acts as a nucleophile
Yep,
and attacks the carbon, and then those electrons go to that other oxygen.
exactly right. Okay, so it's really, really crowded in there, but I'm going to attempt to show this. Okay, we have an acid-base reaction happening in that first step, and conveniently that's actually lined up appropriately. Our serine acts as the acid, our histidine acts as the base. Okay, that next arrow, again, really crowded. We'll try and, I don't really want to use an arrow on that. But in that next step, what we've got is our oxygen acting as a nucleophile, attacking our electrophilic carbon. Okay. And then what we've got is, I'm not quite sure what to call this because all it is trying to account for octet rules. Okay, so we get a pi bond breaking or pi bond cleavage.
When you say like electrophilic carbon, it just has like 4 bonds still. There's no like extra electrons, but you could say that it's like electrophilic.
What does
because all the
electrophilic mean?
offsets are that it wants electrons.
It wants electrons. Okay? Just because it wants electrons does not mean it will be formally positive. A positive atom is absolutely more electrophilic. Okay? But that isn't the only thing. Why is the carbonyl carbon electrophilic?
Because there's a partial.
It has a partial
Oh,
positive
positive.
charge
Gotcha.
because
The dipole? Okay.
both the oxygen and the nitrogen can withdraw electron density through electronegativity effects. Okay, bless you. And again. Well, sorry. Well, there was only one, I think. So, what happens now in our second step? Okay, well, again, our target, the whole goal here is to break our peptide bond. We're trying to, we've got so many colors going on in here, it's going to be hard to signify these. We're trying to break the peptide bond in the middle there. Okay, so we're trying to get this bond to break. Okay, and I'll circle it in red so it stands out. We're trying to break those 2 amino acids away from each other. Okay? Well, in that tetrahedral intermediate, our carbon is now very unstable. We've got 3 electronegative elements attached to it. It does want to eventually grab electrons back. Where can it get those electrons from? Well, the most likely source is our negatively charged oxygen. Okay, so we can do a I want to call it pi reform, okay, for that bond. But if we reform that carbonyl bond, then how many bonds does that carbon have? 5, which is a problem. So we have to break a bond. What bond do we end up breaking? Okay. Now what we'll do is break the peptide bond. But then that puts a formal negative charge on the nitrogen, which is incredibly unstable. Okay. So instead of forming immediately to that, what ends up happening? It grabs the hydrogen from our histidine residue. So what they're trying to show with all these dotted lines is the forming bond. Okay, and really, we could almost break it down into even more steps and say that that nitrogen gets protonated first by the histidine. Once it's protonated, it's now a good leaving group, and now it can be kicked out. Okay, this again kind of goes with the we're trying to cut out steps so that we don't have to look at as much. So that next step is really an acid-base reaction and the bond cleavage all at the same time. Okay? So we really have 2 parts in that next step. We've got a bond cleavage. Okay, and actually, let's switch that around. We can be more specific than bond. We can call that our amide bond. So our amide cleavage and an acid-base reaction, okay, where our acid is our histidine, okay, and our base is our amine, or I'll just call it our nitrogen in this case, okay, our forming amine. Okay. Why did we condense both those steps into one thing? Well, we run into a couple issues here. Okay. Number one, in biochem, one of the reasons why a lot of our reactions happen with high efficiency is that we've now taken everything that we possibly need to get the reaction to work, and we've put it at an exact pinpoint location. In organic chemistry, we can't do that. In organic chemistry, we're looking at doing these things in massive solutions. So if we want a reaction to happen faster, we have to up the concentration in the overall solution to get it to work, but it still happens relatively slow. And that's because we're looking at the concentration of the solution. In biochem, what's the concentration? So it's our moles per volume. Well, our mole amount is very, very small, but what's our volume amount? The volume amount is effectively the exact same size as our mole amount. Okay? So incredibly small. In biochem, our concentration goes from being a few molar to potentially a few thousand molar because the volume is so small. If we up the concentration, what happens to the rate? It increases. So this is one of the reasons why biochem has a big advantage over us. Okay? Yeah.
So when that anide bond breaks, where do all the electrons go? You're saying that?
So what's happening is we take the electrons, and I can really only point, unfortunately, on the screen here. Our electrons from our oxygen go in to reform the carbonyl bond. That carbon now has too many electrons. So what we're going to do is take the electrons in the carbon-nitrogen bond, and those are now going to be shared with the hydrogen. Okay?
Well, first to the nitrogen.
Technically, and that's where we run into issues. If they went first to the nitrogen, that's a bad leaving group, never occurs.
Right.
So really what happens
It's
is
like
the
a
lone
cycle.
pair on the nitrogen pulls the hydrogen off, which makes it a good leaving group, so now the electrons can shift and allow this cascade effect. So you end up seeing kind of a concerted mechanism behind this, which makes it difficult to draw in exact arrows with the exact steps.
So the nitrogen takes the hydrogen?
So the nitrogen takes the hydrogen, which brings in that third arrow that we're seeing there. Hydrogen would then have too many bonds. So what happens with the hydrogen-nitrogen bond? Those electrons go back to our original histidine residue. Okay, so even though we went through and said we've got 3 arrows, and in that second arrow I said 2 steps were occurring, we really have that third step, if you will. I'm trying to not show more arrows. Okay, and that third step, that is strictly an acid-base reaction. Okay.
Wouldn't the nitrogen, since it's accepting a hydrogen, be an acid, since it's going
If you accept a hydrogen, you are a base. If you donate a hydrogen, you're an acid.
I don't know why I still get that confused.
Okay. So this also becomes interesting because our histidine in the first step acted as a base. In the second reaction here, it's acting as an acid. Why? Because we've changed its protonation state. That's why. Okay. So where are we now? Okay, well, number one, we've now got a free-floating chunk of our peptide floating off in solution. Cool, that can be exited from our reaction. But we have another issue. What's that other issue? First, let's answer my question, then I'll answer yours. What's the other issue? We put in a peptide chain. Our goal was to cleave the peptide chain and end up with 2 peptides. How many peptides do we have now? We have only 1. Where's the other half of the peptide chain? It's connected to our enzyme covalently. Okay? That now also needs to get broken off and restore our enzyme back to its active site. Okay? That's what the next sequence of reactions are showing in our next step. Yes?
I just had a question. When you were talking about a substrate, in the book they just show you this little tiny thing, but really a substrate's, from what I'm understanding, it's like a very long polypeptide chain, which essentially, it could be a protein, but they call it a substrate.
The substrate is whatever's being acted on by the enzyme, which could be a very tiny molecule.
Nothing about size.
It says nothing about size. It says nothing about size. Okay? So if we look at ATP synthase, that's ATP to ADP. Those are relatively small molecules. In this case, what are we cleaving? We're cleaving a peptide bond. The peptide bond itself is relatively small, but that's connected to a polypeptide, which could be massive. Okay? So in a situation like this, your active site is probably somewhere on the surface of your enzyme. Because if it's in the middle of the enzyme, you have to thread that polypeptide substrate into the middle of the enzyme to get access to it. Okay? Which could be more difficult. Okay? So in our second sequence of the reaction, okay, we've cleaved off our first half of our peptide. So there's our first half of our peptide. Our second half is still stuck in there. Okay. Well, to cleave that, we're going to have to account, okay, for some oxygens. I can't just cleave out this section of the peptide, because what would the problem be? That carbon would very likely be actually a carbocation. Okay? Well, fine, let's fix that. Let's go through and let's cleave out this section of the peptide. What's the problem with that? Serine is a CH2OH. If I cleave out that oxygen, do I have the OH anymore? Okay, I don't have an active enzyme anymore, and then it's not really a catalyst. Okay? So this means we're missing an atom. Okay? And in particular, we're missing an oxygen atom. Where can we get an oxygen atom? Water. Okay? So in our very next step, what you'll notice that we see water show up into our reaction. That water is helping to go through and break. I don't know why I wrote H2O again. Let's write water. There's our water molecule to go through and help cleave this. We still have to kind of drive everything along and allow for this reaction. Water, while a reasonable nucleophile, is still attacking a pretty horrible electrophile. So we need the water to become a better nucleophile. For the water to become a better nucleophile, it needs to become OH minus. It needs to become negatively charged. But a strong base in a neutral environment doesn't work so well. So what ends up happening is your histidine residue, again, will facilitate the breaking of our OH bond. And yeah, I really, really don't like their arrows.
So it's acting as a base.
Okay. So our histidine acts as a base. Our water acts as an acid. Okay. In that first arrow, we have, I'm not quite sure the best, I'm just going to say acid base / acid base. This is Bronsted-Lowry acid base because we're looking at the transfer of protons. Okay. Where do the electrons in that hydrogen-oxygen bond go? depending on how you want to evaluate this, if we're saying it's happening in multiple steps, they go to the oxygen. If we're saying it's all happening at once, we're taking those electrons and we're immediately having those attack the carbonyl carbon. So we now have in that step our nucleophilic attack. Yeah, our nucleophile electrophile is how I was labeling it earlier. Okay. But then the carbon has too many bonds, so what happens? We break the pi bond yet again. We get our pi bond cleavage. Okay. We again end up with another tetrahedral intermediate, which can then go through again with all this shuffling of electrons. Okay. We can get our pi bond reformation, which then means our carbon has too many bonds. So we kick out a leaving group. Okay, at this point, we don't really have a good leaving group, okay, because the serine would come off as O-. Okay, to make it a better leaving group, we need to protonate it. Well, where can I get that proton? From the histidine residue.
So then you have that concerted.
So again, we have this kind of concerted acid-base reaction. The histidine will then act as your acid. Your serine acts as a base, which facilitates what did I even label that in the previous one? What did I call that? I called it amide cleavage. In this case, it's not an amide, it's an ester. Okay. The net result is that we now have our free enzyme floating out. You'll notice that that's actually kind of odd. I'm not quite sure why they did that. You'll notice that our hydrogen disappeared, okay, off of our water molecule. Why might that hydrogen disappear almost instantly?
Histidine.
Yeah, let me point it out again. So we've got all of our transfers. Okay. Our serines reformed as our hydrogen. We now have our histidine molecule. The histidine, we don't want to be picking up the hydrogen, and we'll talk about why in just a second. Okay. But there's our second half of our peptide. C, carbonyl, carbon, O, H. What happened to that H?
Back to OH.
Okay. No, it's that H. Why is it deprotonated?
The pH probably.
Why would it be pH dependent? What functional group?
It's carboxylic.
It's a carboxylic acid. Okay. So more than likely at neutral pHs, that's going to be deprotonated right away. So what they ended up doing was adding that extra acid-base step and just kind of pretended you didn't need to know about it. Okay? But there is then an extra acid-base step removing that hydrogen to very likely take you down to, okay, RO minus for our carboxylate end of our amino acid or our peptide. Okay? Why not have the histidine pick up that hydrogen? Well, the next sequence of the step is the histidine picks up a hydrogen from serine so that serine's a good nucleophile. If histidine picks up the hydrogen from our carboxylic end, we don't have a base anymore to remove the hydrogen from our serine to allow a turnover of our reaction again.
So again, it's not a catalyst. It's not a catalyst. It stops
You then run
reaction.
into arguments that water can come in and potentially shuttle that hydrogen around. Okay?
Is this pretty much the same for like all?
No.
peptide bonds, or is
All peptide bond cleavage are going to do very similar things, yes. Okay, but depending on what type of chemistry you're doing, you're going to be seeing slight variations off of this. Okay.
it- Does it have a test?
Yes and no. Okay.
The titration curve for last one?
Will I expect you to go through and draw, for this particular question, drawing out this mechanism? No. Will I expect you to draw out a mechanism ever? Probably not. What I do expect you to be able to do is to recognize what type of reaction occurred. Okay.
Acid-base?
So,
like
yeah,
nucleophilic?
that was going to be our next aspect, is what are the different types of reactions that can occur within our enzymes. And this is where I think sapling will get you exposure to a bunch of different reactions. So I'm pretty sure this is yeah, I think this is in the Chapter 7 homework. I can't remember if I've got them grouped or if they're multiple individual examples. But there's at least one question where you will be either given a description or given a drawing and said, what type of reaction is this? And so what you have to be able to do is to say, okay, what type of reaction is it? Is it an acid-base reaction? Okay. Is it a nucleophile-electrophile reaction? Okay. Did it react with a metal ion?
So it'll show you like the stepwise with the arrows?
What's that?
So it'll show you with the arrows, like what
It may
happened,
or
and you
may
have to
not
interpret
show
it?
arrows. Okay, so that's also going to depend on this, and that's ultimately because biochemists are horrible with arrows, so the odds of anybody actually showing you an arrow is very unlikely. So what you have to do is interpret what the overall image happened through it. Okay? So with that, that's where we kind of run into some reminders of your definitions. Okay? I personally find these definitions ridiculously important, and I will test you on these. Okay? And they can be as simple as, what is a Bronsted-Lowry acid? Okay? So I need you to know what's happening with each of these, because that's what's driving all of our chemical reactions, is what's happening at each of those stages. If you're looking at just the transfer of a hydrogen, okay, if that is the only thing that occurs, you're now a Bronsted-Lowry acid or base, okay, depending on what your direction you're going at. Okay? If something else occurs on top of an acid-base transfer, that's when you start moving into your other definitions, electrophiles, nucleophiles. Okay? And within electrophiles and nucleophiles, that's where you can run into the different types of reactions. Substitution reactions, addition reactions, elimination reactions. Yeah. Isomerization does get listed in there, but isomerization is really just a separate class of one of the others. Right? Yeah, that's just leveling up the difficulty of the question. Okay. So within those, acid-base, substitution, addition, elimination. Those are your four primary categories that you're concerned about. If you remember from organic, there was a fifth. What's the fifth?
Elimination.
Did I not say elimination? I did say elimination.
E1, E2, substitution.
Acid-base, substitution, elimination, addition.
Oxidation, reduction.
Related to that,
Reduction.
radicals. Radicals is an extra reaction. Depending on which organic you took, you either saw or didn't see radical reactions. We don't need to worry about radical reactions, because typically when radical reactions occur, you get lots of high energy intermediates. If we're thinking biology, do we really want lots of high energy intermediates? So anytime a redox reaction, or not redox, a radical reaction occurs in the body, that gets kind of dangerous. Okay, think about free radicals. Everybody panics. Oh, there's free radicals. There's radicals everywhere in your body. It's going to happen. Okay? We don't want free radicals. We want them to occur in very tiny locations where we can control them. Okay? So you aren't going to be responsible for looking at your radical reactions.
So acid-base, substitution, elimination, addition.
Acid-base, substitution, elimination, addition, which brings up the next question. Can everybody see those, or should I write those out as an example? Because I don't think they're in the slides.
Not even in the book.
I don't think they're listed in the book either. Yeah, so here, let's pull it up. Acid-base, what are you looking for?
Lewis acids and bases?
Yeah.
Nope. So when I say acids and bases, I'm really only referring to Bronsted-Lowry, because Lewis acids and bases covers everything. It is pretty meaningless to look at Lewis acids and bases, because every single reaction is a Lewis acid and base reaction.
Yeah,
Okay,
that's
so
what I
it's
found.
pretty useless definition. So when we're looking at acid-base reactions, I'm referring to Bronsted-Lowry. That's the transfer of, got a little French there and a little transfer. Transfer of protons. Really what you're looking for is the exchange of a hydrogen from one location to another. Okay. There are ways that can be hidden that makes it tricky. Substitution reaction, usually written as SN. Why SN? It usually involves a nucleophile. So it's substitution for S and for nucleophile. What are we looking for?
SN1 or SN2?
We don't even care about the mechanism.
And what does the SN stand for?
And then we can
Substitution nuclear substitute.
So if we're looking at just a general reaction, you end up with AC and then B floating off. Your nucleophile, characteristic for a nucleophile,
Once a positive charge.
so its charge is negative. So we can tag some more information in here, which then your B is going to end up being negative as well. Okay. Your elimination reaction is going to be a little bit harder to do. Whoops. I'm not sure why. What happens in your elimination? You have the formation of a pi bond. Okay. We're going to run into issues with using different variables here. X typically refers to as a halogid, but what I want you to be aware of is your elimination does not have to be a carbon-carbon double bond. It can be a carbon-oxygen double bond or a carbon-nitrogen double bond. Okay, so X in this case is just referring to really any atom. Okay. In the process of doing this, we form the double bond between carbon and whatever X is. We'll almost always lose an H plus, and you'll have some leaving group as Y minus. Okay. If you go back and look at that previous reaction that we just did, we did some elimination steps within that. Okay. And then your addition. We start with a pi bond and we end with not a pi bond. So we're adding usually H plus, that's an H, and some nucleophile. Okay. So elimination, you're looking for a pi bond forming. Okay, that's your product. Addition, you start with a pi bond and you lose the pi bond.
So you're adding that H and the Y for addition?
You're adding the H and the Y across the pi bond. Yep. Okay. Questions on that? Those are general forms. Of course, it gets more confusing because it's not just a carbon sitting there by itself. We got 60 other things attached to it. Okay, so you tend to freak out and look at that. So look for where the change is occurring. Ignore everything else. Okay. Tail end of this chapter talks about coenzymes, which is kind of how you get into your redox reactions or your radical reactions. The two big common ones are NAD plus and FAD. Why do those get interesting? NAD plus is in the exchange of going from NAD plus to NADH. Why is that an interesting reaction? I heard somebody say something, proton transfer.
I said electron transfer.
Oh, good, electron transfer. It's not a proton transfer. If you look at the structure, you'd say, oh, I added a hydrogen, so it's got to be an acid-base reaction. But for an acid-base reaction, we have to add H plus. We start with NAD plus. If you add H plus, it becomes plus 2. This is coming neutral. What are we adding? You're adding H minus. Okay. How you add that H minus? Well, remember H minus is something that's incredibly reactive. We don't actually ever form it in the body. So what ends up happening is you get the transfer of 2 single electrons and an H plus. Okay, so you go through a radical mechanism to transfer the electrons and an H plus. So your structure ends up changing. About the nicotinamide, so as far as the name breaks down, it's nicotinamide adenis. Maybe it's just How does that NAD break down? I don't remember. This is the structure, though. Okay, so you've got the nicotinamide section, which is really where your chemistry is happening, is right here. Okay. The rest of that is connected through some sugars up to an adenine. Okay. Yeah, I was going to attempt to make up another name, but that doesn't work. Okay. So the chemistry that ends up happening is if we look really, really carefully right there at that nitrogen, what charge is it? It's a positive charge. So what ends up happening in the course of your reaction is we take a single electron which then puts a lone pair on the nitrogen. And the most stable location for that radical is actually sitting on the very top. Okay. We get a second radical coming in, giving us a negative charge on top of the structure, which then picks up the H+, and what we end up with for our NADH is this guy. There's our NADH form. Okay. The rest of the structure maintains the same. Okay. So all that's really happening is that nicotinamide is changing its structure, and we're adding our hydrogen up at the top. Okay. Why do we add it up there? It has to do with resonance and all sorts of other fun stuff, and since I forgot to draw, there's your lone pair on your nitrogen as well. Okay. So you're looking at some fun transfers of electrons to facilitate that. If anybody, actually I think I will be talking about it after spring break when we look at our biochemical pathways. We'll talk about the redox reactions of nicotinamide and FAD to FADH2. Okay? So these tend to be common coenzymes. They're involved in reactions because we're looking at transfers of electrons. Those transfers of electrons can actually facilitate other reactions. So we're forming a high energy intermediate that can then dump stuff off onto other things. We get a lot of chemistry coming out of these. Other things that can happen, you've got a lot of B vitamins. They can go through and help facilitate the transfer of an amino group. We could go through and look at the mechanisms on those, but I don't think it's going to be all that particularly relevant. Okay, so all of those help facilitate the transferring of an amino from one location to another. Also known as transamination. That is the end of chapter 7. Questions?
You make it sound easier than what the book says.
I cut out a lot of stuff
Chapter
too.
7 is like, what?
If you think chapter 7 is rough, you should look at which I'm actually kind of interested to see what happens, because almost nobody's talking about any of the DNA, RNA stuff. So I'm going to be doing some real whip-through kind of rough lectures on that after spring break as well, to kind of cover those bases, because you guys decided that wasn't interesting. Okay, fine. I can accept that. Okay. And those chapters are rough.
What, for DNA and RNA?
Yeah, particularly when you're looking at operons and how they work.
You are going to go over that, right?
I am going to talk about those, the key aspects that I think are the hardest. What I'll do is skip over the stuff that's just, the ribosome has this unit, and it has this unit. And if it's a prokaryote, it has this one. And if it has a eukaryote, it has this one. Because
Is an operon basically a sequence of nuclei?
we'll talk about it.
Okay.
We'll talk
Is
about it.
that, yeah, that shows up.
Are there questions on chapter 7? Kind of okay with that?
Is that gonna be on the test? Coenzyme?
How it goes on the test, I don't know. I don't know yet, because at this point it's pretty much just memorization. When building the test, what I will end up going through and doing is probably relying pretty heavily on the sapling homework and on the practice exam. Okay.
For the second test?
For the second test. So very similar to the first test as far as formatting, except I'm probably going to be pushing more towards using some of the sapling homework to get some new problems in there. The reason why I'm relying so heavily on the old stuff, I've got 3 exams to write for next week. I've got a wedding starting tomorrow through the weekend, and then I don't have any of the exams written. So it will probably be very, very similar. So again, make sure you read the questions carefully, because there may be very subtle changes in those exams to get you to different answers. Okay. So with the practice exam, it's not a bad idea to use it, but what you should do with it is, okay, how are other ways you could ask this question? Could you say not? Okay, that kind of stuff. Then chapter 16. The first half of chapter 16 is a bit rough. If you guys remember chirality from organic, you get a lot of kind of chirality discussions and different ways to represent and draw structures in chapter 16. The second half of it is just examples of what are a whole bunch of different carbohydrates. So it's ultimately just memorization stuff. So what I'm hoping to do is that we will be able to get through kind of the nasty stuff of our enantiomers, diastereomers, and the relationships between structures today, so that next week is just kind of the memorization stuff of what are individual carbohydrates. Okay? So your carbohydrates are ultimately saccharides. Okay? Well, your saccharides are just a combinations of carbons, hydrogens, and oxygen in a particular ratio, or an approximate ratio, that we then classify as a saccharide or a carbohydrate. Okay? Your carbohydrates are polymers of these individual units of your saccharides. So some of the other terms you may hear are polysaccharides for your carbohydrates, because we're just saying there's more than one saccharide molecule within it. Okay. Most of them follow the general formula shown, where you have the same number of carbons as you've got oxygens, and then twice the amount for your hydrogens. By definition, you're varying from 3 up to 8. So you can have as few as 3 carbons and be classified as a saccharide, and you can have as many as 8 carbons. Okay. Those then get further subcategorized into 2 separate sections, either aldoses or ketoses. An aldose because
Aldehyde?
the highest order functional group is an aldehyde. Ketoses because the highest order functional group is a ketone. Okay? So that's your primary subcategorization between those. Okay? And your polysaccharides or your carbohydrates are just putting in a whole bunch of these individual repeating units and connecting them in very particular patterns. Okay? And that's where a lot of the second section of this is what are examples, carbohydrates, and then potentially how do they react. So our absolute simplest example of our saccharides would be the triose. What does that tri for? That means there's 3 carbons. So what if we moved up to 4 carbons? Tetros, 5 carbons. Pentose, 6 carbons. Hex, hept, oct. Okay. So that gets you the class of your saccharide, or your class of your carbohydrate. Okay. But realize that even once you're in that class, you can then separate into aldoses and ketoses. Okay? So each of those can then subdivide out into different categories. They further subdivide, which we'll get at once we move into more complex examples. So with the 3-carbon sequence, we've got 2 possible saccharides that come out of this. Okay? You get the, I think they call it the aldotriose, or aldotriose, or the ketotriose. And what, again, we're trying to do is mash all that information into one name. Okay. We get glyceraldehyde and dihydroxyacetone. Both of those are common building units. The glyceraldehyde becomes more important just because of its chemistry, and in particular, one extra thing. What is that one extra thing that's important on glyceraldehyde? What was that?
Besides the OHs?
The dihydroxyacetone has 2 alcohols too. What do you mean position?
Not necessarily their
It's
chirality, it's just the structure of it.
It's exactly the chirality. This carbon is a chiral atom. It has 4 distinct things attached to it. You've got the carbon of the carbonyl, the oxygen of your OH, the carbon of your other alcohol, and a hydrogen. That is a chiral carbon, which means not only do I have just glyceraldehyde, but I have 2 forms of glyceraldehyde. If we look at the dihydroxyacetone, there is no chiral atom. Okay, so at this level, for the trioses, we really have 3 trioses. We have 2 glyceraldehydes and 1 dihydroxyacetone. Well, what happens is we add more carbons. If I just add 1 more carbon in an OH, what did I just add? Another chiral atom. If I add another carbon in an OH, another chiral atom. So that means each of those positions we'd have to be very specific about which form of chiral atom we had. Was it R or was it S if we pushed to organic chemistry? Was it wedged or was it dashed? Because as soon as we change it, it's now not the same structure, potentially, And we have to worry about naming that new compound, and it's now, of course, going to interact with our bodies differently, because what happens with our bodies? Our bodies are chiral. It's going to respond to those in different forms. Okay? So if you look at a lot of the, not fake sugars, but that kind of idea, the artificial sweeteners, okay? What has happened with those artificial sweeteners? They've changed some of the chiral atoms, okay, which changes how our body interprets them. And in particular, it changes how our body turns them into fat. Okay? But it still has the proper chiral arrangement that we can acknowledge it as sweet. We just can't process it, so our body just excretes it, okay, as opposed to actually holding on to it. So it's kind of the idea behind taking advantage of these chiral atoms. So we need to come up with some way that we can represent these. Because if we go through and show wedges and dashes on all of them, that can be a bit tedious. So what ends up happening? We move to Fischer projections. Okay? And those of you that had any interaction with me as organic chemists know that I hate Fischer projections. Okay? I don't know what any of your other backgrounds are when it comes to Fischer projections, but most organic chemists tend to not like them because we don't have to work with them. Biochemists love Fischer projections because this is just the two possible options for a triose. If I jump up to a tetrose, I've now got 4 possible options. That's a lot of wedges and dashes I have to draw. So I want to come up with some easier way to represent and draw this. That's Fischer's model. Okay? So what Fischer went through and did is came up with some orders on how to rearrange and redraw these. I don't remember if I've got this nicely drawn. I don't have that nicely drawn. So what we do is we rearrange our structure. So we take our highest priority carbon and we put it at the top. Where's our highest priority carbon in both of these? It's our aldehyde carbon. So for both of these, I'm going to draw them where our aldehyde carbon is up top. Okay. The carbon chain is then always going to be drawn on the vertical axis. Okay. So I'm going to end up drawing it straight down. Okay. Well, how do I know how many carbons there are? Carbons are usually specified with points. If I just draw straight down, I don't see any points. But what can I do? I can add a point by drawing a cross across it. As soon as I've specified that cross, I now have a point. I now have that extra carbon there. Right? So if we take a look at the leftmost one, I have another carbon atom there, so I'll draw it there. The other carbon atom is at the bottom of this, and it's connected to an OH. Okay? I don't have to do that one with a cross, and we'll talk about why we don't have to do that one with a cross. So we can add the other one here with our OH at the bottom. The trick now is that we have to make sure that we put in our H and OH in the appropriate spots on either side of that. Right? To do that, you must be drawing it as a Fischer projection. So what does that mean? Our carbon train is always written on this vertical axis, and it is always aimed away from the viewer. Okay? So if we added some more information in here, these are dashed bonds. Well, if those are dashed bonds, what is our cross? Those are wedges. Okay? Which means none of our atoms are in the plane. Okay? Why look at it at this viewpoint? Well, the reason being is that if you are always in this formation, do you need to specify the dashes and wedges? If you're always in the proper Fischer projection, where Fischer says your backbone is always aimed away from you and these are always aimed at you, well, then you don't need to specify the wedges and dashes, because by definition, that is where they are. Okay, so we could ultimately simplify them down. The next question is where to draw the H and the OH. So if we take this structure, how do we get it into this format? So these two carbons must be aimed away from you. They are currently in the plane of the board, right? So to get them aimed away from you, right? Try that again. My body doesn't quite move. So there's our carbon triangle. Okay? To get it aimed away from you, my fingers are now aimed away, right? What happened to the OH? The OH was aimed at you, right? If we go through and do that same manipulation to get the carbon chain aimed away from you, where's the OH aimed? To the right. But what if I had rotated, can I do this? I'm freaking out. Let's just do that. If I rotated the other direction, whoops,
Yeah.
Yeah,
that
there
way.
you go.
There it is. Okay. Now it's on the left. But am I looking at it in a Fischer projection?
No, because those.
No, because the carbon bonds are aimed at you. Okay. So there's that, but then I could have gone like that, right? Oh, God. It's still aimed
Yeah.
at you. Or, oh, God, how do I get my hands to do this? There, I think it's that. Now it's also on your left. Okay. But what's the problem?
Upside down.
It's upside down. Fischer projection, your highest priority must be
At the
top. So when we do this rotation down, this highest priority index finger has to come up that way, right? Which means this OH being wedged is always going to show up on the, our right-hand side. If we go through and do the other one, what you'll notice is the OH ends up on the other side. Okay. We now have a way to represent these relatively simply, and what this usually gets condensed into, actually let me just erase everything. Condensed into is OH, aldehyde, CH2OH, H. Why do we not need to specify the other OH on this weird axis? No.
Because the Fischer projection always tells you that your straight line or your backbone's away from you, so
Okay.
it doesn't matter.
Why am I not doing this? We're only including the chiral atoms within that. That last carbon is not chiral, so I don't need to worry about it. Okay, it doesn't need to be drawn on that axis. Okay. Fischer went through and started to compare things and came up with his own kind of R and S system. Okay, if you remember R and S, you had to have the correct viewpoint on your structure, aimed everything away, or then we brought in optical activity, and we said dextrorotatory versus levorotatory, or positive and negative. And we used lowercase d and lowercase l. We said R and S are an entirely separate system. Don't confuse them, because they have different rules. Well, guess what we introduce now? Another system, which is, again, completely separate from R and S and completely separate from our optical activity. Okay? So it would be nice if we used a completely separate, different set of terminology. But we don't. The symbols we use are capital D and capital L, not to be confused with lowercase d and lowercase l, because lowercase d means the molecule rotated light to the right. Capital D means the OH on my my last chiral carbon is on the right-hand side of my structure. Capital L means my last chiral atom has my highest priority group on the left-hand side of the structure. Talk about arbitrary systems, okay? But that's what's happening within it. Why does this become important? Well, what happens if we scale up to more complex sugars? Ooh. We've got erythrose. We've got more carbons in here. This is D-erythrose. Why is it D-erythrose? Look at the last chiral carbon. Where is the OH? On the right. That makes it D. D-threose. The OH is swapped to the other side. Why is it D-threose? Because at the last chiral carbon, it's still on the right. What happens when we look at, where is it? are L-urethros. The last chiral carbon, the OH is switched to the other side. Okay?
Majority are D though, right?
The majority are D. Okay, so it is very rare to actually see L pop up. Okay? It's only mentioned because it can show up, but in biological systems you deal with D. Okay? You'll notice we talked about aldoses, we talked about ketoses, we talked about trioses and tetraoses, and yet when you look at the names of those four compounds, you don't see an ald, you don't see a ket, you don't see a tri or a Greek prefix. Why? Because F biochemistry, that's why. They created new names for each of the sugars, or each of your possible sugars. Okay? I do not expect you to memorize those names. I do expect you to be able to use the Greek prefixes and then the ald versus the ket, okay? And then the D and L nomenclature I expect you to use. When it comes to your online homework, you may be asked, which of these is D-urethros? I'm not asking you to have that memorized. I'm asking you to look it up, okay? And verify that the structure matches. Your homework, you're supposed to have access to this background information. It's supposed to be there to help you get through it. So use that. Okay. The next thing that we can pop into is we could now potentially bring in this whole concept of enantiomers and diastereomers. So enantiomers are stereoisomers that are mirror images. Your strict definition for enantiomers, anybody remember?
Choosing groups?
No. It does have to have a chiral atom, but so do diastereomers. Yeah, the flipping of your hand's kind of the right idea. The relationship, we have to have them be mirror images of each other, and they have to be not superimposable. So it's two parts, not superimposable and mirror images. So if you're looking at two structures and you see them as not superimposable and they are mirror images of each other, they are enantiomers. How do you know they're diastereomers? They're not mirror images and they're not superimposable, which, said another way, means it's not different, because different is a whole separate thing. That means a different formula. They're not enantiomers. So if you go through and look at a classification and you decide that everything kind of matches up between them, okay, but they aren't mirror images of each other, they're diastereomers. Okay? So, oops, sorry, don't mean to freak you out with that one quite yet. So, triose versus triose, the relationship is diastereomers. So what we would try and do is say, first off, is there a mirror image? So if I put a mirror in between there, are they mirror images of each other?
No.
So they're not mirror images. Are they superimposable? Take this, try and slide it over on top.
Nope.
The OHs don't overlap. So this is one of the reasons why Fischer projections are nice. If you remember back to organic, we could flip and rotate and mess with the structures as much as we wanted. With Fischer projections, you don't, because then you're no longer in the Fischer projection and you're back to dealing with all the crap you had to deal with in organic chemistry. So Fischer projections make things a little bit simpler to see those relationships because you're locked into that Fischer projection viewpoint. Okay? So, what if you have more than 4 carbons? Oh, that's what that slide was supposed to show. This is what happens if you have 4 carbons. You get 4 possible products coming out of this. Okay? Or 4 possible arrangements. You'll notice that urethros is a special molecule. Why is that a special molecule? It's a meso compound. Or, no, it's not a meso compound. Oh, we're just missing the L-triose. That's the problem. Okay, so the L-triose, the L-triose isn't shown up there. Okay, but we could draw out the L-triose as well. Okay? When we move up to more than 4 carbons, well, you get 5 carbons. Okay, you got pentoses, 6 carbons. You get hexoses. Okay? That urethros, triose, and all of that fun stuff, this is your origin of those names. So if you have just 1 chiral carbon, you're looking at a glycerol, okay, as your root name. If you got 2 chiral carbons, you're looking at urethro as your root name. 2 chiral carbons where the OHs are on the same side, you've got urethro. Okay, where the OHs are on opposite sides, you got trio. Okay. you have 3 chiral carbons, the individual arrangements of those. Okay? So it snowballs, and they now have each of these kind of pseudo backbones named in each of those circumstances. It's a pain to deal with. Ultimately, you're not responsible for that. What I want you to do is be aware that that is going to show up in your homework. You just got to look it up. Okay? And then make sure that everything matches within that. We could look at it as subdivisions down within families. Okay? So this is your aldose family tree. There is the equivalent for your ketoses. Okay? But this kind of shows each of those patterns on what happens as you add an extra carbon, how that translates through. And you'll notice that what ends up happening is when you go through and add your carbons, you're adding them in slightly different fashion, which generates all those different structures that come out of it. So when we're looking at our carbohydrates, there are a ton of possible carbohydrates. Please do pack up, and I'm not offended if you walk out. I just really want to quickly talk about this. The next thing we're going to address is this issue between alpha and beta, which happens when we cyclize a saccharide. Okay? That alpha and beta is looking at the OH with respect to your CH2OH. Notice that in this case they're on the same side of the ring, which means we have a beta. If they're on opposite sides, we have the alpha. Why do we have 2 possible products? In the cyclization process, your oxygen is attacking a carbonyl carbon. It's attacking an sp2 carbon, which means that alcohol can attack from the top, in which case the OH aims down, or the alcohol attacks from the bottom, the OH aims up. Okay? So not only do you have D and L, you have alpha and beta, which comes out of the cyclic form for your saccharides. Okay? We will pick it up there on Tuesday. That is a bit challenging to deal with, so please read up on that because you're pushing kind of into the exam. Okay?